let's think about gates and impulses, okay? So the difference between gate and impulse, anyone? Gate signal and an impulse signal?
It's a 1 or 0 on or on off.
Yes, and the impulse is?
It can be varied over time. No.
Impulse is 1 just for a very moment.
Yeah, exactly. Impulse is supposed to be an instantaneous kind of jump in frequency, whereas the gate actually has a significance to its duration. Yeah? So typically a gate signal is something that sustaining envelopes respond to, envelopes that require 2 triggers, whereas a trigger would be suited for just a triggering envelope, or if you use it for a sustaining envelope, obviously the sustained portion would be nullified.
So
okay?
you say, so in an analog domain, I mean obviously a gate, does it have a duration? Do they specify how long it should be open for, or is it just...
Well, let's test it.
Okay.
Yeah, because I mean the point is that in the analog domain what you get is these non-velocity sensitive keyboards which do just this, you know, while it's held you get the voltage, you release it, you lose the voltage. So that's where it all comes from, really. But let's test it. So I have an ADSR in here, and then what I'm gonna do, well, let's just look at things for now. This is my second channel, okay? So what I'm gonna do is take, I'm gonna be looking at this signal as well. Where the hell did this one go? Okay, so this will be that output, and then I have another one of these. So I should have a square type wave right there. I'm gonna take the lowest frequency possible. Actually, this one goes much lower. Okay.
So I just ask a quick question.
Please do.
You'll say with those keyboards, like on an MS-20 or something, when you hold the key down, it keeps that open the whole time, right? So you're saying the gate just stays open.
Yeah.
So the gate is just, as long as you hold the keyboard down, the gate is on.
Right,
yeah. That's why you get that continual, and then you can affect it and do what you like as the signal's just going through.
Yeah.
Okay.
Yeah. Okay, so I have a really slow square wave here. It's a bipolar one. Yeah, so again we can see how things respond. Normally you would expect an envelope to be 0 and then some kind of positive threshold in terms of the trigger input. And that's also something we can test, remind me please, in terms of what is the triggering voltage for a certain, for this ADSR. Because you expect it to have a kind of a positive threshold. If you cross this threshold with the voltage, it assumes that that was the attempt to trigger it. And if you don't, then you don't. So we're going to test that in a second, yeah?
But are you saying that ADSR stays open in this?
That's what I'm about to find out.
Yes.
Yeah, it should stay open while my gate is open. Yeah. Okay, so now I'm sending this signal. So you have the actual gate signal on top, and then in the bottom you get this signal. Now this might be because my sustain level is 0. Okay, so I've increased my sustain level slightly. And there it is, you see? So it was actually holding for the duration of the gate. So I have the attack portion, decay portion, kind of a sustain. I can try to make this even longer. So this is my width. Okay, so you see it actually sustains, waits for the gate to come off and then comes down. Yeah? So that's your typical operation of the gate. Bit of a brain exercise. What would happen to this signal, or actually what would be the product of multiplying these two signals? Which bits of the envelope would I lose and which I wouldn't?
Do you release
the release I'm definitely losing, yes indeed. How about the other stages?
Attack.
Well, attack, that's questionable. Would I lose the attack?
Does it depend how long it is? Because
well, I mean, the envelope is derived from the pulse wave. So this is my pulse wave. And then the envelope I get from this cannot start before this initial jump, which means that I would indeed catch the attack portion. Yeah? And then if we multiply it such that the pulse reaches the unity gain and back to 0, yeah, then you would get the exact same envelope, except indeed here it would shut it off before it could potentially produce a release stage. Okay? All right. Cool. Now the interesting thing about this envelope, by the way, is that it's fairly cool because I have different ranges. So you can actually observe what happens if my attack and decay time are too long. You see, I never even reach the sustain. And I potentially don't even reach the full voltage here because I'm going down already. Okay, little gates. Right, so let's discuss briefly then. Well, we can actually test. Let's dig a bit more into envelopes, especially the one that I have here. Obviously, I didn't spend much time promoting modules up till now. But what I have here is a really nice beast, which has 4 envelopes. And it has a way of making them consecutive, running in a cycle. Yeah? So what I have there are only rise decay, attack decay envelopes. So I have only 2 phases. So let's look at one of these. I will remove this. So what I have, and let's trigger it. Was that it? Yeah, you saw it happen. Okay. Make it a bit faster. Okay, so that's my envelope coming in. So you see, I don't have any triggering. Maybe it would be better if I induced the triggering just to be able to control that separately. So here's my pulse wave for the trigger. It's a bit high, this frequency. Let's take this one. Okay. Yeah, you see I'm triggering this rise decay envelope. And then the nice thing is that actually my second one is, this one is the first, this one is the second. So this is my first envelope, and then the second envelope here, what it allows me to do is make it come after the first one. So essentially what you get is that the envelope trigger is normalized to the threshold. Yeah? So the thing is, the word normalized is very often used in modular synthesis as a descriptor, and what it means is that 2 things are connected unless you plug something else in. Yeah, this is a kind of a very common behavior that you will find. So typically what I expect here, I'm not quite getting it, let's see what's going on. This envelope, probably the threshold, here it is, okay? So if I'm a bit late, I'll make both of these envelopes kind of similar shape. Let's take the time base. You see? So I actually have a way of making sure that the one envelope follows the next one. And then I can change this threshold to essentially move the 2, and I can get to the point where they trigger at the same time. Or I can make it such that the threshold is very low. So you see, essentially what I'm doing is I'm thresholding this. Let me just make sure I'm saying the right thing. So the original envelope is channel 2. Yeah, so this is the original envelope. So what I'm doing is I'm thresholding it, and if my threshold is fully left, yeah, then I get this in sync, and then as I turn it right, I get the secondary envelope to be more and more delayed. So the top one is the secondary one, and there could be a point where I don't even get it triggered, but I'm not there. It doesn't do that. But you see now it's almost caught up with the previous one, so you get this kind of effect. What would be interesting about this in terms of sound synthesis? Well, it could be that let's see what is the frequency limit. Huh? So if I take both envelopes to fully as short as possible, you see I almost get pulses now. I'll take it such that the one is somewhere in the... Oh yeah, because what happens now, you see, because it's a pulse, I don't get the delay to the secondary envelope. Does that make sense? So it shows you that the trigger for the secondary envelope is dependent on the amplitude level of the first one. And if the first one is only an instantaneous jump, then I cannot get this kind of delaying envelope effect. Only if this was an actual decay, then based on that decay, I could set a point where the second one triggers. But regardless of that, the reason why I took them down is to test the frequency, okay? So maybe this is also worth listening to. Let's hear these envelopes as they sound. I think my purple thing was the output. Okay, so this is my envelope at a very... Okay, so I'm increasing the frequency. Okay, so what you see first of all is that as I increase the triggering frequency of this envelope, what you are looking at is the actual so the second channel is what's coming out. So I get the unipolar signal that's expected from an envelope, 0 to positive values, and then as I increase the frequency, that's a funny point. Why would that ever happen? So you see, this so far it's expected. So if I have a very low frequency, let's try to see that as well. I have like a full wave, full range output almost. Let's just make that a 0 as well. I think my things are offset since I've played with the FFT. So I have a 0 to about 7-8 volts. Now this is the setting of the shortest envelope, and you see that the decay time is actually longer than the attack. Now if I increase the frequency of the triggering, what you see is that the 0 point starts to climb up. You see, that's because it doesn't have the time to fully release, it's triggering itself again. And then at this point it seemed to, it dropped again. See, I'm monotonously increasing the frequency. So if we really want to test this, what we can do is we can automate the changing of the frequency. Okay, with the, this one is not very slow. That's a problem. I might have to do it by hand. Actually, I can try to do it with this ADC. If I can find a slow way of triggering it. Probably not. No, I could do with if this is a separate one. Okay, let's try. So I have a very slow changing of frequency, hopefully. See, there are anomalies there. So it's not just the actual waveform of the envelope. There is something funny going on there as well. Okay, we could attempt to, before listening to this actually, just do a basic high-pass filter on this, just to avoid the DC offset. Okay, let's try this and actually probably scope that, because it might be that the DC offset through the mixer does funny things. Yeah, so now we've discovered that there is an anomaly here, but we are not sure if it's down to the modules. Okay, so here we go. Hello. I pass. Did we? Okay, so we've lost the DC offset, we've lost tons of gain as well. But it doesn't really serve us too good. Let's go back to just looking at this. Okay, and if I... This is a really funny point, you see, because it's actually changing, it's kind of jumping in frequency. Okay, so, but conclusively, actually this goes up all the way. I mean, as far as all the way goes. Does it read the frequency? Channel 2. See if it can read the channel 2 frequency. This is... That's this one. This one. Yeah, in any case, what you can conclude is that it goes up fairly high. So let's just quickly change this to this ADSR here. So we had an input. You see, this one doesn't really do those frequencies at all, the ADSR. Now I'm in the higher range. Yeah? Cool. Okay, so shall we have a short break? How is the brains? Let me just check the time. Might be worth... Huh?
8:25.
Oh yeah, already?
Yeah.
Okay, let's give it a little break. I mean, you guys are welcome to come here and talk about stuff. And we could come up with the last little thing. There are a few things that I wanted to get to. We're a bit late with most of these things. But by all means, if you need a toilet, take a few minutes.
Look at this, this thing's awesome.
Nice. Go out to watch an experimental jazz group do James Blake theme nights.
Is that tonight?
Yeah.
Where is this?
Galamalfrey.
Oh yeah?
Just up the road.
Oh, cool.
So I'm heading after this.
That'd be good though.
Actually, it's the band Waldo's Gift. They're one of the bands I booked for our second year broadcast gig that we're putting on.
Cool.
They're pretty good.
Yeah?
They're interesting.
How experimental is experimental?
It depends on what they're doing, because sometimes they're a bit rocky. They're kind of like jazz meets math rock. You know what I mean?
Oh, cool.
Like one guy wanking over his guitar and a drummer playing out of time.
Out of time, you mean complex beats? Yeah? That's my kind of thing.
Yeah. Like trinomial guitar. Yeah.
You really sold them well, man. I might have to go off with you. Are you cycling or did you?
No, I'm walking because my house is only a few minutes away. So
yeah.
just walk down. But yeah, should be good.
Cool.
Go to Galamalfrey, take out a mortgage and drive home.
Is it expensive?
That's like
Really? It's the place next to Blue Lagoon, isn't it?
Yeah. I never go into the Blue Lagoon, not unless I'm looking for a fight.
Is it that bad?
Mate, I've seen so many fights in that fucking place.
Really?
Honestly,
So rowdy.
Yeah, it's rowdy, rowdy place.
I've only been once in the night, and it's just totally not what we expected. But I live right around the corner and go quite a lot for like brunch and stuff.
Yeah, it's alright, they always play music on the music as well, it's just...
Yeah, I've been to the open mic a few times.
Whenever I go there, they always just I don't think it's definitely, I mean, I thought it was my first. Yeah, Gallimouth was nice. Yeah, just a bit.
It's a bit of a party place, really.
Yeah, I suppose so.
Kind of place where you let loose.
It's just where everyone goes, it's got far too much money. Can't really afford it.
You could smuggle some booze in, yeah?
Just spend money anyway. Just don't have my bank account.
I'm actually a bit...
Forget it exists.
I might give it a skip, actually. The weak side. These 3 weeks of my life are the busiest. Now with the UE and this as well.
Yeah.
It is heavy. Okay, let's try to finish off with some interesting things. I mean, one of the things we could do is deal with the logic a bit and see what kind of modulations we get from that. I mean, as far as being properly analytical, we don't have the kind of FFT or the kind of understanding of this oscilloscope to read out, although it should give us that thing, to read out the sidebands and then read out the amplitudes and all of that. But it might be interesting. First thing that I wanted to just briefly go to, as which is potentially will increase our understanding of what waveforms actually mean, because it's not as straightforward, is let us think about this waveform. Okay, so I have a kind of a square wave with a steady period. So you all understand that a fixed period means that the pitch is fixed. Now, if I move this flank back and forth, which is my pulse width modulation, then the pitch stays fixed as well. That's cool, I guess, yeah? I changed the timbre. Actually, the interesting thing to know is that if this is bang on in the middle, I will have only odd harmonics. As soon as I move it off the 50% point, I will start getting even harmonics as well. Yeah, so there is that's one of the crucial changes, and the other one is as I approach the impulse, I will get more high frequencies, louder high frequencies. Yeah? Now, what I'm trying to get to is this other scenario where I have the same square wave, but what I have here is that one of the peaks is slightly lower and every other is slightly lower. And the question is, will this produce a pitch change or not?
Well, the phase hasn't changed.
Well, what do you mean phase has changed?
You know, the difference in your cycle is still the same.
Yeah, this is the same cycle. It is just that
It's just that's lowered, yeah.
it's just that one of the peaks is lowered and the other one is still high.
So you get attenuation in. So
You get the attenuation every other cycle. So would this give us a pitch change or not? That's the question.
Would it just give you a perceived pitch change?
Well, pitch is a perceptual phenomenon to start with.
Yeah. But what I mean is, the picture isn't changing because you're not actually changing the frequency of your cycle.
Any other opinions?
Does the whole two segments sort of act like one? Is that
See, that's the counter argument. We have both arguments here on board until we patch it, obviously. And I'm a bit ambiguous as well. You know, sexually I'm straight, but as far as these kind of arguments go, yeah. And the funny thing is that You see, actually this relates, before we patch this, honestly I have no idea how we're going to do this, but at least we can discuss that. But something that is slightly related to this is this phenomenon, which is really interesting, called the missing fundamental. So if you have a harmonic series like that, and you filter out these frequencies, you filter out the fundamental, maybe the first few harmonics, you listen to this signal, you still hear a pitch corresponding to this frequency.
So the pitch hasn't changed?
The pitch hasn't changed. Yeah? The funny thing is, I'm almost sure about this, but I'm a bipolar as well, yeah? That if you FFT this signal, you can not even forget about playing with filtering it out, because that's a kind of you don't know how much attenuation, maybe minus 80 dB, it's still there, it's kind of ambiguous. Just synthesize these sine waves, put them through FFT, and you will get a spectral peak at this position. We're gonna have to test this one. I'm almost sure, but I think that was the case last time I looked at this 10 years ago.
What?
It has to do with the periodicity. Because you see, if I have, this is the third harmonic, the fourth harmonic, the fifth harmonic, the sixth harmonic, if you draw out all these harmonics, the only point when they actually come back in phase will be the period corresponding to the fundamental frequency. So this whole idea of the missing fundamental, I think we can question this. Maybe it's our ground for paradigm change in psychoacoustics, and telling them, no man, I'm sorry, but as far as, if the FFT shows you the frequency there, why would you ever say that it's missing in the first place?
But do you hear it differently? I mean, I know you
hear it differently, but you still hear the pitch. The pitch.
You hear the same pitch, but you
hear a different timbre, obviously.
Yeah, exactly.
Yeah. But the pitch is the same, whereas supposedly, and that's this kind of true phantom problem, because technically we did not synthesize this sine wave, but because we synthesize all the harmonics, they will produce a periodicity in that time frame. You see, because I'm not that good with drawing, but if you just look at one of those graphs when you have like the second harmonic, third harmonic, fourth, all the harmonics, you just forget the first two, and then look at the point where everything kind of lines up again. It will actually be related to this period duration. So that's one thing. Let's write a paper about it. That would be so funny, to just tell the psychoacousticians, sorry guys, the FFT knows it's there, so it is there, no matter the fact that you think that you haven't synthesized it, which is a kind of a funny thing. Okay, so back to this. Let's try to synthesize this. So how do we synthesize this thing where we have a square wave and then every other period I have a bit of attenuation going on. So if we think about it, let's first think about it. What we really need is to multiply two signals. So one signal is the actual original square wave, and the other signal has to be high here, and then slightly lower here, and then high here again. Does that make sense? So this is actually a square wave of half the frequency. Make sense? With offset attenuation such that it does something meaningful to the previous one. And now we're already getting to, you see, actually to synthesize it, I already have to take an oscillator which is half the frequency. Is there any other way of synthesizing this? I mean, technically, if we've done it with multiplication, you know the maths, we should be able to do it with addition as well. What are the two signals added together that would yield such a signal? One and two. Make sense? So, what is the frequency of these two signals that I'm adding now?
They're both the same.
They're both the same. They're actually half the frequency. It's just that they have this offset in terms of peaking, and obviously the pulse width is funny as well. So you see, actually, and this is a typical math thing, you could express it the same outcome, the same final signal, with multiplication and addition. You see, that was the thing that we talked about in terms of sidebands as well, because if you add together 100 Hertz and 110 Hertz, yeah, there is an equality between this addition and a multiplication with 10 Hertz, with a difference frequency. Yeah, so if we dig up the trigonometric of this, we can probably kind of derive it, and it all falls into place. And this is a similar thing, but you see here now that actually here we multiply frequencies, two different frequencies, and here we add two of the same frequencies, and we are getting the same kind of signal. I'm not sure which trigonometric thing would possibly give us the equation between these two.
When you say they're the same frequency but one's slightly...
There is a phase offset between the two.
But also lower, right? Because that one...
Yeah, lower. That's what we're trying to do ultimately. Yeah, this is lower gain, higher gain, bit of delay. So which one should we try? Green or red? I think I can do the green one fairly reliably, and then we can see if we can do the red one as well. Huh? Potentially, I'm not quite sure actually, because I have... This one has a sync input. We're going to talk about syncing. No, only this one has a sync input. So we'll see about the addition-based synthesis, but let's look at if we can do this through multiplication. So the way to do this is to work with the frequency divider. So let's meet the frequency divider beast. So I'm having my original signal, my primary square wave here, okay, first channel, and then I take this into the frequency divider. Let me just make sure I'm triggering off that as well. Source channel 1, source channel 1, here we go, okay, so that's my initial square wave. And then what happens if I take it through? Aha! There we go, it's there already. Nice and neat. So, and actually my setting is currently at half or 3. Yeah, so now I have the, so to speak, zero frequency division. Yeah, so it's not divided. And then, which is funny because then I'm dividing by 0 supposedly. You see, designing modules isn't easy on their end either, you know, because if you say I have a divider, you cannot start the parameter value at 0, can you? Because that's meaningless. Okay, never mind that. So now if my dial reads 1, I actually should have this halving thing. So I can change the trigger to channel 2 just so it's fixed. Oh, I hoped it would be. Just a second. It's my trigger here. Okay. Yeah. So now I have divide by 2 at the setting 1, and then I'm hoping to get something like divide by 3. Yeah. And so on and so forth. So I do have this kind of option here. So back to our little idea of synthesizing such a waveform. We have half the frequency. Note that my input is bipolar, almost reaching 5 volts, and my output is strictly unipolar, 0 to 5. And this goes back to actually using digital chips, I would say, as far as my understanding goes, that it doesn't really respond to the continuous voltage in any other fashion than yes or no. Yes or no, okay? Good, so the thing that I need to do in order to produce this type of signal that I've imagined to be cool and questionable in terms of pitch is to season this signal. So we have this half frequency square wave, and what we do with it is we make sure that instead of it being 0 to 5 volts, we can now make this whatever, around 5 volts, 6 to 4 volts. Yeah, so we get this kind of offsetting, okay? And then finally what we need to do, and that's why we spent the first hour with figuring out whether we have a multiplier today, we need to multiply the two things, yeah? So I'm gonna take, actually probably best if I keep, I'm just thinking about what am I monitoring, so we have a nice little display. Oops, that's a wrong idea. Okay, so here we still have that signal, okay? And here we have the original square wave, okay? So what we do is take that square wave into the X input here, and we're gonna take the frequency half signal into the Y input, and then we are going to listen to this lot. Listen to this lot. I just said listen to this lot. Okay, so, and now the output should look the way we've imagined it to be, which it is not really looking like. Let's see. What was my setting for? Oh yeah, that was my setting. Okay, X, Y. So the Y input, this one, if I remove it, yes. And then, okay, here we are. So it's almost there, but it's not really the way I drew it, yeah? We're gonna think about why that is in a second. I think I know. And this is obviously very low frequency now, so yeah. So this is the signal that we've produced from this one. Yeah. So there is a definite addition in terms of the frequency content. What about the pitch? Anyone can sing? Yeah, I think we could agree that we get a signal which is an octave lower. Yeah? Okay, so that mystery is now solved. Yeah, we know that if we do this, then the actual period length is doubling as soon as there is an anomaly. Yeah, if we introduce this little anomaly, actually this is not the sketch anymore, but we had this little anomaly in the amplitude, and no matter the fact that we would by basic intuition say, oh well, it's the same square wave, it is just, you know, every other time it's a bit different, this every time a bit different does do the octave halving. So this is the basis of all your kind of subharmonic distortions and such. Interesting, how does this frequency divider work? Well, there is such thing as counters in basic electronics. Yeah? So that's essentially how it works. We won't go into that. But there was one thing that I wanted, oh yeah, we have to discuss, I mean, it's not necessary, but it might improve our understanding of stuff. Because you see, the original waveform that we wanted to synthesize was a bit like this. So one up and then one lower, one up and then one lower. And instead, we've got this funny thing where we have a small jump and then a big jump which goes below this one. So again a small jump and then a big 2 jump like this. You see the difference?
Could you add a pulse of a quarter of the frequency?
Quarter of the frequency?
Because you're using a quarter? Hang on. I'm trying to figure out.
Well, the two component signals did look like what we wanted them to look like.
It drops out the bottom, which is the bit you don't want, isn't it? Ideally. where it drops lower.
So why? But that's the question. Can we figure out why? Well, it has to do with the fact that we are suddenly in a bipolar setting. Yeah? Because what you get is that this is, you see, what I have as a control signal here, yeah,
Because you're saying that one's
this is the higher one and this is the lower one. So this stage of amplification will both push this one up but also push this one down, because a negative voltage amplified is a negative voltage.
So if you change that,
But that's a yes.
if you change that amplification amount to nothing, then the frequency will appear an octave above. Can you test how, like, if you just do it fractionally?
Well, that's why I'm also still puzzled about this. So hopefully we're gonna come to the bottom of it, because as far as I see my signals, I actually have the original signal. So let's call this the original signal, yeah, starting at 0 volts. You see? So that's why I'm puzzled, because if no matter how much gain I put to this 0 volts, it shouldn't pull it lower down. You see? So it might be, let's just check the polarity of all our signals in here. So my two component signals are, let's see, what am I looking at? So this is my first scope, okay? So I have this original square wave, you see, and it's bipolar. And then I have the actual frequency divided square wave, and this one is unipolar. Okay? So what we can predict is that if we make this original waveform, where is this one going? Here. Yeah, so this is the bipolar one. So if we make it unipolar instead, by essentially offsetting it, okay. You see? So if I make it an actually unipolar signal, it's funny, there's something, oh yeah, I think there is some, oh yeah, this is a problem, I just do this, okay, because I had some feedback in the patch. Okay, so if I, oh yeah, shouldn't do that, instead do this, right? So the top is my original square wave. Now if I make sure it's at 0 line, you see I get the kind of waveform we were after. It's inverted, but that doesn't really hurt us. This is the next question. If I make this one strictly positive, doesn't reach the 0 line, why do I not get the halving anymore? Oh, I just sold it. Yeah, you see, because if this is my original square wave, yeah? If it's kind of centered around 0, let me increase the gain of it, yeah? I get this type of waveform. If I manage to get it down to 0 line, you see, it will actually make the kind of waveform we were after. But as soon as I get above the 0 line, I don't get any difference anymore. Why would this be? I have one guess, which is that it actually stops the frequency divider from working. Okay? So let's finish this lecture, I think, slowly by looking at this frequency divider. Okay? So let's test it. How are we going to test it? Well, we're going to put a pulse wave through it. Are we on time? A bit over the
10
time?
minutes.
10 minutes left. Oh, cool. So what I want to do now is test this frequency divider in terms of when it is triggering. So we understand already that no matter what the range of the input signal is, it will output strictly 0 to 5 volts. It doesn't have any other way of responding to a signal. Yeah? but we are suspicious of it not triggering if it doesn't cross the 0 line. So typically you could have, in a digital system, triggers are always 0 line. If a signal crosses from negative to positive, it's called a trigger. Now, actually, we will probably have the time to test the envelope with the same technique, because in the analog domain, typically envelopes would have a fixed threshold at maybe 3 volts, maybe 5 volts. So you have to cross that value in order to make it trigger. But it might be that our frequency divider here is either. So the only way to find out is to take a square wave, then this is the square wave that I'm plotting in one channel. So in the top channel I have my original square wave. Okay. And well, I have obviously the range and offset controls here. And then I'm gonna look at the output. And then based on this offset, you see it's still triggering, Now it's not triggering. Okay. Oh, now I'm having issues with the trigger. Sorry, I'm just gonna. Oh, that's another thing I don't know how to do with oscilloscope, is switch off the trigger mode. Not very handy. And I've tried to prepare. I promise I looked at the manual RTFM. You know the song. And it's just too convoluted. It's just when you see 200 pages of manual for like 5 dials and 10 buttons, you're like, they've squeezed too much into it. And it's all for the love of analog gear anyway. Okay, so what we've done here is we're trying to look at when this thing is triggering and when it is not. So if my signal now crosses the 0 line, so back to the old setting, so the 0 line is here, halfway the top, so now it's crossing the 0 line, I'm triggering, now I'm increasing the DC offset, and you see now I'm above the 0 line and it stopped triggering. And the same thing holds if I decrease the DC offset fully, then also it stopped triggering. So we can conclude that this frequency divider actually triggers at 0 volts. And then the other thing which might be interesting to know about it is, when does it break? Does it break? In terms of increasing frequency. So now we're listening to it. So it seems like there is some anomaly to it. I think I have a larger range on this one. So you might say expectedly it doesn't really break. However, is it clean throughout? With this one there was more. You see, there is something really funny about it with this one. Maybe because of the pulse width. Okay, now we're talking. This is getting interesting. So what I have here, I'll save you from the beautiful noise, is source channel 1. Okay, so, oh, that's interesting. So the top one is the original signal, and what seems to happen is that as I increase the frequency, oh, it doesn't really happen. Okay, change the pulse width. It's not really a sharp flank, you see. As far as the pulse waves go, I would imagine a faster transition right there. But what I seem to have discovered now is that if I change the pulse width, I change the timbre of the divider. And that's puzzling. Well, obviously that's not puzzling because I'm just dropping below 0. Why does this happen? Well, we can't just see it now. And if I change to channel 2, trigger. Okay, so now we can see it potentially. You see? So the pulse width modulation comes through my frequency divider. Yeah? So it seems that it's not only watching for the up flank, it's actually waiting for the second drop as well. You see? Is this right? Let's just... Yeah, so what you would expect is that this flank going up would be a kind of fixed point. That's where it starts to trigger. And then you see that it's actually not releasing after the first... Is this right? CV1, 2? Ah, okay, so this is half the frequency.
That's 1.5 there, right?
No, this is the actual frequency.
But the other one
This is the half. Okay, so actually now we're getting there because that's why it was a bit funny, because you see it is it starts going up when the period starts on the first trigger, and then it waits and drops it when the next trigger comes in. Yeah. So triggers are typically only transitions from negative to positive. It doesn't trigger both ways, only on the going up. Yeah. So it first trigger makes it go up and the second trigger makes it go down, in which case the pulse width modulation does not come through. But if I take the third subharmonic, which is this one, so what happens now is that seemingly a down flank is the one that makes it reset. Oh, this is funny because, oh yeah, that's this one. So actually now the two down flanks are making, and that's why the pulse width comes through. Let's see with this one.
Which one was that? What was that?
So that was the third subharmonic.
Right.
Yeah, so 1/3 of the frequency.
Yeah.
So in the same way we have a harmonic series, we have the subharmonic series. Yeah. So divide by 2 is the second harmonic, divide by 3 is the third one, fourth, and so on. Huh? And you understand that the intervals related to these divisions are given. They're not just octaves. Yeah, just like the harmonic series is not octaves. So you get the fifth and then the fourth and all of those. But it seems like, okay, so now I'm...
On the odd ones, it's doing on the down, and on the even, it's doing on the up.
Well, yeah, I guess so. But you see, this one is fixed, and this one moves. But this one also is actually lined up with a downward flank. You see, this is also...
And what's this one?
This is actually an upward flank, so this is the fifth. Yeah, so you see that's how it operates. Might be useful. Frequency divider lets the pulse width modulation come through on such occasions. Okay, and what did I mention about the... Oh yeah, so let's just check the envelope, the triggering threshold for the envelope. So we understand that my the frequency divider has a 0 volts triggering threshold. Yeah. So now let's look at the envelope. It might be very high frequency. Let's take the lower frequency. Okay. Right. So the top is my triggering signal, and then the bottom is the envelope. Okay. Now everything is 0 on the envelope, pretty much. Well, that doesn't really matter. I can make it a nice little envelope as long as it attack, decay, sustain. Okay, it looks like an ADSR. something like that. Okay, so let's now play with the triggering signal. Well, first of all, it's really loud, okay? So now I'm below the 0 line, it doesn't trigger. Now I'm going across the 0 line, and it seems to trigger already. Now I'm increasing further, and it seems to be changing the amplitude. Have you seen that? So as soon as I make this a bit larger, so again I'm back with my triggers below 0. Nothing going on. Or actually I should call it a gate because it's an ADSR control. So now my top of my gate signal reaches slightly above 0. And I'm starting to get a little bit of an envelope. And now I increase it above. Now I'm at about 3 volts. I get a larger amplitude envelope. So you can conclude that there is actual response to the peak of my trigger. So you could call this a velocity sensitive envelope, which is a useful thing to know, because otherwise you'd expect, oh well, it's not, which means that you can actually control this by scaling the input signal. By the way, if you scale the output signal, you get the same thing again. So it's not necessarily useful like that, but in other situations might be. Okay, so and now what I've noticed also is if I go far above, so it's still triggering, and I seem to remember that there was a point, still above. Okay, now I'm reaching the point when my lower flank is above 0, and you see my lower flank is above 0 and it stopped triggering. Now I may now ask, does this have to do with the lower amplitude level crossing 0, or it has to do with the upper amplitude level crossing some other imaginary threshold, about 5 volts, and obviously I can find that out if I increase the amplitude here. Okay, and then again I'm gonna work it above 0. Well, can't do it just like that. Okay, and you see now that actually I am above 0, I'm below 0. It seems like there is just a little bit above 0 that makes the triggering stop. And this technically is called a Schmidt trigger. So what Schmidt trigger normally does, it does not allow re-triggering before you drop below a certain point. So it's a kind of dual trigger mechanism. So there are 2 thresholds normally. One threshold is for producing the trigger, and the other threshold is the reset threshold, which makes sure that you will not re-trigger the envelope unless you drop below a certain level. Now in this case, what it seems that both levels are the same, because if I drop completely below 0, do I remember right? Yeah, it doesn't trigger. Above 0. So the really confusing thing is that I'm now actually slightly above 0 and it's still triggering, and I have to decrease the amplitude. Oops, sorry, this one. So now it's stopped triggering at about, well, almost at what is this, 1 volt actually, because that's 10. So it seems like I've got this threshold around 1 volt. So just to make sure it's a different threshold, to make sure if it's a different threshold, let me go down back below 0, just to see if I can make sure that that is actually the 0 point where it starts triggering. Okay, just there. Yeah, I'm slightly above 0. Okay, it is the same trigger point at 1 volt. That's where it starts responding at 1 volt. Okay, and then what we could also do in terms of, okay, let's make this a full understanding of what's going on. So if we could look at the maximum value for the input trigger that still makes a difference. And in order to do that, I'm going to have to do this twice. I don't have sufficient gain in one stage, so I'm going to do it twice. Okay, So this is, you see now I'm actually running it higher. I have that bit more gain now. Okay? And you could see that actually the peak of this envelope is currently at 8.5 volts. And if I decrease the trigger signal, I keep decreasing it. It's still 8.5. I keep decreasing it, it's still 8.5. Keep decreasing, it's still an 8.5. There should be, you see, so actually it doesn't go all the range. It's still 8.5, still 8.5. Okay, now it's gone. That's 8.5. Now it's gone. It's a very, very tight. It almost seems like there's only two kind of variations, like a full envelope and a half envelope. There's a very small difference there. But you see, actually, my trigger top has gone down to 2.5 volts. So it seems that this amplitude response, this kind of amplitude sensitivity, only holds between 1 volt and 2.5 volts. You see? So those are the typical things that you need to be able to find out if you want to use this accurately, if you want to set up a patch which will produce a change in the envelope like that. Okay? Cool. I think we're about done. Any questions? Cool. Well, I hope to see you all on Friday then. Thanks for coming. Yes.